Let's talk about air. What makes up most of the air you breathe? Ask the average person on the street. I'll bet they'll tell you oxygen. No, not even close. If the air were mostly oxygen, every time somebody lit a match, the whole room would explode. Oxygen is incredibly flammable. So in fact, atmospheric air is a bunch of different gases, okay? Each contributes what's called the partial pressure. So air has a certain pressure here at sea level. We call it 1 atmosphere, all right? But each one of the gases contributes to part of that pressure, okay? So that's the partial pressure. So at sea level, 1 atmosphere of pressure is 760 millimeters of mercury. Remember that crazy way that we measured blood pressure? Back in the old days, the sphygmomanometer had a big giant column, glass tube, actually full of mercury, and you would watch the level of the mercury in the tube go up and down. So air pressure, there's really better ways to measure it, but this is an old-fashioned way, still somewhat in use. 760 millimeters total of mercury, all right? Now, alveolar air is a slightly different mixture of gases, and that makes sense, doesn't it? Because you're doing gas exchange in your lungs. Remember, the waste, your cells, all right, are creating the waste product of carbon dioxide, okay? So therefore, in your lungs, when you are, when you're doing the gas exchange, the capillaries are releasing tons of CO2 into your lungs. So your lungs have a much higher concentration of CO2 than the outside air does, all right? And atmospheric air is humidified by the respiratory cavities, all right? We add water to it, so we also have more water vapor in our lungs than is in the outside air. And gases are exchanged and mixed with residual air. That's why, for example, on a cold day, you can see your breath, people say. What that actually is that's water vapor. You're exhaling water vapor, and then because of the cold air, it's condensing, and so now you can see it. It's basically a cloud. You're making little clouds is what you're doing. That's what's happening when you say you can see your breath. You're making clouds. So take a look quickly here at the table on the left. Notice nitrogen is about 79% of the air here on planet Earth, okay? We have a nitrogen-based atmosphere. Oxygen is right around 21%. Water, maybe 0.5%. CO2 actually makes up hardly any of atmospheric air. It's only 0.04%. That's 0.04%. So that's far less, 4/100ths of 1%. Notice then that look down below at the total line. So you see the total amount is 760 millimeters. Well, see how nitrogen made up 78.6%. So 78.6% of 760 is 569. That is the partial pressure of nitrogen, all right? Do you see how we do that? Oxygen at 21%, roughly 20.9%. That's 159 millimeters of mercury. Notice then that oxygen makes up 159 out of 760. So 159 divided by 760 is 104. Oxygen, you can see on the left the inspired air, and then on the right the alveolar air. So you're seeing the difference. So you're seeing the partial pressures, all right? 597 for nitrogen in the atmosphere, 569 for nitrogen in your lungs. Notice therefore the oxygen is there's more in the outside air than there is in your lungs. And why is that? Why is there more in the outside air? All right, well, sure, that's because when you breathe in the oxygen, you're taking it into your body. You get what I'm saying? So outside air is 20.9% oxygen. Air in your lungs only 13.7% oxygen because you took that oxygen out of the air into your blood. And then notice again at the bottom, CO2. CO2 only 0.04% of atmospheric air, right? Inspired air is the atmospheric air. And then notice though, in your lungs, it's 5.3%. That's because all that CO2 in your lungs is CO2 that you made in your cells, and you're trying to get rid of it, okay? So the air-water interface, all right, so look at oxygen here. Look at oxygen, all right. We see oxygen dissolving, all right, into an equilibrium state, the initial state, the equilibrium state, and then down below we see carbon dioxide, the initial state and the equilibrium state. So what does that all mean? Well, let's take a look. Air-water interface important for gas exchange between air in the lungs and the blood in the capillaries. Because remember, your blood is 50% water. So the ability of these gases to dissolve in your blood is a big deal, all right? Because that indicates how well they can get in and out. Gases diffuse down their concentration gradients, just like everything else in nature. So Henry's law says the amount of gas that dissolves in water is determined by its solubility in water and its partial pressure in air. So here's what it comes down to. Let's just summarize this. Carbon dioxide is a lot more soluble in water than oxygen is. So carbon dioxide is easily carried in your blood because of its solubility, all right? On the other hand, oxygen is not as soluble, but it has a much greater partial pressure than carbon dioxide. So oxygen can dissolve in the blood because of its partial pressure. Bottom line is both oxygen and carbon dioxide can be carried dissolved in the blood. Remember, that's not the way you carry most of your oxygen. Most of your oxygen is carried on hemoglobin, but some can dissolve. Again, the problem is oxygen is not very soluble in blood, but because of its higher partial pressure, some can dissolve. Carbon dioxide, on the other hand, is easily soluble in water, and therefore that's why you remember how carbon dioxide was carried in your blood mostly? It's carried as the bicarbonate ion, but it can be dissolved in the blood as well. So factors affecting gas exchange, concentration gradients of gases. So the partial pressure of oxygen, 104 millimeters of mercury in alveolar air versus 40 in blood. This is what I was saying on the last slide. So think about it. When you breathe in air, the air needs to go into your blood, right? Well, the oxygen in the air you just breathe in has a partial pressure of 104 millimeters of mercury. The oxygen in your blood, because it's relatively poorly dissolved, is only 40 millimeters. Remember, gases always move down their gradients. So what's going to happen? Oxygen is going to move from higher pressure to lower pressure. So therefore, where is oxygen in your lungs going to go? It's going to go from the air in your lungs into the blood. The pressure is literally pushing oxygen into your blood. Do you see what I'm saying? Pressure in your lungs of oxygen, 104, pressure in blood only 40, therefore oxygen naturally kind of forces itself into your blood because it always flows from high pressure to low pressure. On the other hand, carbon dioxide. Carbon dioxide is much lower out there in the alveolar air, but in the blood, there's much more carbon dioxide because remember, you're creating that carbon dioxide in your cells. So in this case, notice the carbon dioxide, the partial pressure in the blood is 46, whereas the partial pressure in the air is only 40. So which direction is it going to go? It's going to go down its gradient, and therefore it's going to go from the blood into the air, all right? So notice the exchange of oxygen and carbon dioxide in the lungs all has to do with pressures. It's precisely because of the difference in pressure. Oxygen flows from the air in your lungs into your blood because the pressure forces it that way, and carbon dioxide flows from your blood into the air in your lungs because, again, the pressure forces it that way. So gas solubility, CO2, as I mentioned on the last slide, 20 times as soluble as O2. So oxygen gets into the blood because it has a greater concentration gradient. CO2 can get into the blood because it has greater solubility. It's the pressure that forces it to move from one to the other. And then as a result of the pressure, oxygen relies on its concentration to stay dissolved in the blood. CO2 relies on its solubility to stay dissolved in the blood. So tidal volume, approximately equal to what? 1 shot glass, 1 wine glass, 1 can of arrogant bastard ale, 1 pitcher of beer, or 1 keg of beer. Make sure you know your basic respiratory volumes. Do you remember tidal volume? What was that? That's how much you breathed in and out with each breath. Yeah, that's roughly 16 ounces. And there you go, arrogant bastard ale. Pretty good. It's, it's not the greatest, but it's not bad. Not as bad as like Budweiser and Coors and Miller and crap like that. I'll occasionally get an arrogant bastard ale. I enjoy them, so. All right, so here you go. This diagram, this illustration on the left, oh my God. You should sit down and spend, seriously, about 15 minutes with this. And just look at how the differences in pressure, the tissue fluid, systemic gas exchange, deoxygenated blood, alveolar gas exchange, gas transport, expired air, inspired air, alveolar air, oxygenated blood. This is how oxygen and carbon dioxide are moving around. It's always because of the pressures. Just look at the pressures and you can figure out which way things are going to go. So spend some time. Notice down at the bottom we have the capillaries, that's systemic gas exchange, and up on the top we have the lungs, that's alveolar gas exchange. So notice how the pressures are very, very different at alveolar gas exchange and at systemic gas exchange. Notice in systemic gas exchange, we're going to be forcing CO2 into the blood and O2 out of the blood, the pressures are, whereas in the lungs it's going to be the opposite. The pressures are going to be forcing oxygen into the lungs and CO2 out of the lungs. So it's all about pressures, all right? Has to do with things always moving from greater pressure to lower pressure. And you can see that the pressures are very different between the lungs and the tissues of your body. Seriously, spend a little while on this diagram. It will pay you back. It really will. All right, so alveolar gas equilibration and RBC transit time. So it takes gases about 1/4 of a second, 0.25 seconds, to equilibrate. In other words, for oxygen to move into the blood, for CO2 to move out of the blood. All right, we're in alveolar. All right, oxygen takes about 1/4 of a second for oxygen to get into the blood. Takes about 1/4 of a second for the CO2 to get out. Now you might wonder, oh my gosh, is there enough time? Is that enough time? Well, at rest, all right, normally a red blood cell will take 3/4 of a second to pass through an alveolar capillary. So does it have enough time? Sure, it's got plenty of time. It only needs 1/4 of a second to do the gas exchange, but it's there for 3/4 of a second. So it's got all the time in the world. But what about if, like, you're really exercising strenuously? Is there going to be enough time now? Yeah. Even at vigorous exercise, red blood cells are staying in alveolar capillaries for about 0.3 of a second, 0.30 of a second. We only need 0.25 to do the gas exchange. So even sort of at maximum exercise, there's still plenty of time to get the oxygen in, okay? So oxygen transport in arterial blood, we talked about this when we did the blood. So most of your oxygen, by far, 98.5%, is bound to hemoglobin, all right? 1.5% is dissolved gas. Remember, oxygen doesn't dissolve well in water, and so that's why we have hemoglobin. Hemoglobin is precisely because oxygen does not dissolve well in water. Therefore, hemoglobin transports the oxygen, all right? Only a little bit is as a dissolved gas. So binding to hemoglobin, each heme group has 4 globin chains. We remember that? We saw that before. So each molecule of hemoglobin can hold 4 oxygens, okay? 4 oxygens, 4 molecules of O2 per hemoglobin. So we talk about when air is just leaving your lungs, we have what's called oxyhemoglobin, HbO2. Hb is for hemoglobin, O2. So when your blood is fully oxygenated, we call it oxyhemoglobin. Then when your blood is not oxygenated, we call it deoxyhemoglobin. We call it HHB. H is for hydrogen, all right? So notice in oxyhemoglobin, we've got oxygen that's bound to the hemoglobin, and deoxyhemoglobin is hydrogen that is bound to the hemoglobin. Then the oxyhemoglobin dissociation curve, all right? Relationship between hemoglobin saturation and PO2 is not a simple linear one. So after binding with oxygen, hemoglobin changes shape to facilitate further uptake. So in other words, once you bind one oxygen to hemoglobin, it becomes more receptive to binding another one, and then more receptive to getting the third and the fourth. So hemoglobin actually sort of like sucks oxygen onto it, all right? The more oxygen on the hemoglobin, the easier it is to get more on, okay? Then, I skipped past that, I didn't mean to. What will happen is then when we get into the tissues, the acidity of the tissues shifts the oxygen hemoglobin dissociation curve. and now the hemoglobin wants to get rid of the oxygen. So what happens is in the lungs, hemoglobin is actually wanting to grab oxygen, whereas in the tissues where it's more acidic, where the pH is different, hemoglobin now wants to get rid of oxygen. And so that's what happens. Now, I mentioned this before when we did the blood. At rest, you only usually get rid of one of those 4 oxygen molecules. And why? Well, you think, well, that's very inefficient. Why would we do it that way? Well, that's so that when you start exercising more vigorously, when you're running from the chupacabra, you have a reserve. You know, when you have to start using more oxygen, you've got more to use. So only like 1 at rest. When the chupacabra is chasing you, you might be using maybe 3 or even 4, okay? So that was oxygen. Now CO2, transported in venous blood, most of it as carbonic acid, and specifically as the bicarbonate ion. So remember, I've shown you this little relationship before, all right? This chemical expression here. CO2 plus H2O makes H2CO3, which is carbonic acid, and that dissociates into the bicarbonate ion and hydrogen, all right? So this is the way, so we are seeing the equation running from left to right, all right, the relationship. It can also run right to left, okay? So it runs left to right, all right? We're going to dissociate that when we are in the tissues. When we get into the lungs, we're going to run that from right to left. We're going to turn the bicarbonate ion back into CO2 and then exhale it, all right? So bicarbonate ion is the way that you transport most of the CO2 in your body. You transport some of it on the hemoglobin molecule, but look, only 5%. Look at the tremendous difference here in what's going on between carbon dioxide and oxygen, which was what I was talking about a few slides ago. The overwhelming majority of your oxygen is carried on hemoglobin, only a tiny bit in the blood. Look at carbon dioxide, just the opposite. Most of it is actually transported in the blood, and only a tiny bit is on the hemoglobin. Binds to the amino groups, not the heme group. Doesn't bind to the iron. It binds to the protein chains, the amino acid chains on the sides. And then as a dissolved gas, as actually gaseous CO2, some of it travels that way as well. But most of it, by far, is as the bicarbonate ion. So systemic gas exchange, we need to, so think about it, systemic means out in the tissues of your body. We need to get CO2 out of your interstitial fluid and into your blood so that we can take it to your lungs to get rid of it, all right? So we need to load CO2. So carbonic anhydrase is an enzyme inside of the red blood cell that catalyzes this reaction, the one we saw before, okay? So we have what's called now the chloride shift, and this is really, really cool, all right? Keeps the reaction proceeding, exchanging HCO3 for Cl minus. So look in the lower illustration. I know it's very small, it's hard to see, but look at what happens here, all right? Look at the carbon dioxide coming into the red blood cell, all right? So on the left-hand side, we see the respiring tissue, it says. So in other words, this is going to be your interstitial fluid, all right? CO2 from the ISF is going to be crossing the respiratory membrane, right? Remember, we saw that before, size of a racquetball court. It comes in, and then it's going to go into, it's going to diffuse into, remember, gases easily diffuse across membranes. It's going to diffuse into the red blood cell. So now you see CO2 plus H2O, because there's water inside, right? And then see CAH, that's carbonic anhydrase. So this reaction, this CO2 plus H2O forming carbonic acid, that will happen no matter what. But carbonic anhydrase speeds it up. There's an enzyme that makes the reaction take place much more quickly. So once CO2 enters the red blood cell, it becomes H2CO3. Remember, you don't have to know any chemistry, just count letters. When CO2 plus H2O, you've got 2 H's, 1 C, and 3 O's. So H2CO3 is carbonic acid. Remember then, all acids dissociate into hydrogen plus whatever is left over. So notice it dissociates into HCO3 minus and H plus. Well, here's the deal. We want that HCO3, that's the bicarbonate ion, we want that now to travel to our lungs where we're going to blow it out as CO2. This is just a temporary way. The bicarbonate ion is just a temporary way to transport the CO2. So what we want to do is we want to kick it out. So we kick it out of the red blood cell, all right? So, but notice when we kick it out, we have kicked a negative ion out of the red blood cell, and we put an additional negative ion into the blood. Well, that's not right. We've got to keep the negatives and positives balanced. So what happens when we kick out a bicarbonate ion, a negatively charged bicarbonate ion? By golly, we take a chloride from the blood. Why would we take a chloride? I wonder, what's the most common anion of the extracellular fluid, of which, of course, blood is extracellular fluid? The most common anion is chloride. You got a ton of chloride in the blood. So this is the chloride shift. Do you get it? Chloride comes from the blood, goes into the RBC, and the bicarbonate ion goes from the RBC out into the blood, all right? So we are now keeping the negative ions balanced. But the other cool thing is we now put the bicarbonate ion out there into the blood, all right, where it's going to be able to travel back to the lungs. But then notice we have this hydrogen left over. So what are we going to do? Well, by golly, look what's going to happen here. That hydrogen is going to go down there, and it's going to bind to the hemoglobin molecule. And so what it's going to do is it's going to kick the oxygen off of the hemoglobin so that the oxygen goes out into the tissues, and then the hydrogen will grab a hold of the hemoglobin and form CHHB, that is deoxyhemoglobin. So do you get that? You should follow that through a couple of times on your own to make sure you got to back up and listen to this as many times as you need to, okay? Because that's how we exchange gases in the tissues of your body, all right? So hydrogen binds to hemoglobin, forming deoxyhemoglobin, and then we unload the oxygen. Hydrogen binds to the HbO2, decreasing its affinity for O2. Remember I said that once we get into an acidic environment, hemoglobin is less likely to hold on to oxygen. So hemoglobin arrives 97% saturated, leaves about 75% saturated. So as I said before, you've got every hemoglobin molecule can hold 4 oxygens. Normally, at rest in the tissues, we only kick one of them out. So the hemoglobin stays 75% saturated. That's called the venous reserve. So once again, in case the chupacabra chases you, you've still got 3 oxygens on that red blood cell. Or in case you have a heart attack and suddenly you're not pumping any blood, you know, you're going to lose consciousness, you're going to get too weak, you're going to collapse onto the ground, your body's going to go horizontal, all the blood will spread itself out evenly, and all of those hemoglobin molecules still have 3 oxygens left on them. So they can continue to supply your tissues with oxygen for a while. That's why you don't die usually immediately after a heart attack. You've got a little bit of buffer there. You got time for the ambulance to get there, for somebody to start doing some CPR. Because of the venous reserve, even deoxy blood still has most of its CO2. It's still 75% saturated. Patients who suffer from myocardial infarction can still deliver oxygen to their tissues for several minutes. Okay, that was systemic gas exchange. That was in the body. Let's look at what happens in the lungs. And basically, it's going to be just exactly the opposite, all right? So having gone through that once, it should be easier. We're just now going to do it in reverse. So reactions are the reverse of systemic gas exchange. We have to unload CO2 and does all that binding. The reaction, the chemical reaction runs in the opposite direction. And now we have the reverse chloride shift, okay? So look again, look at the little in the lower right, look at that diagram down there. So now we're in the lungs. Let's look at the oxygen, all right? Remember, oxygen is going to be coming in because of the difference in partial pressure. There's much more oxygen in the lungs than there is in your blood, so therefore oxygen basically forces its way into your blood. Now it's going to diffuse right into the RBC, right? Because gas is diffused right across membranes. So now the oxygen is going to come into contact with that deoxyhemoglobin. Well, here in the lungs, we're in a very rich oxygen environment. So now hemoglobin has a very high affinity for oxygen. It wants to grab the oxygen, so it does. And look what it does. When it grabs the oxygen, it kicks the hydrogen off, And that hydrogen therefore gets kicked out temporarily, all right? Then look what happens now. Before we did the chloride shift, now we're going to have a reverse chloride shift. At this point, the bicarbonate ion is going to come back out of the blood into the red blood cell, and we're going to kick that chloride. We've been carrying this chloride since we were out in the body. We've been carrying that chloride. Now when we get to the lungs, we're going to kick it back out again, back into the blood. So again, we're totally balancing the negatives. We're going to pull the bicarbonate back into the red blood cell and kick the chloride out. That hydrogen that we just got rid of off of the hemoglobin, it's going to grab that bicarbonate ion. That's going to turn it back into carbonic acid, and then carbonic anhydrase is going to speed up the reaction, and by golly, we will turn that bicarbonate ion back into a CO2. And again, it's the difference in pressure. There's much greater pressure of CO2 in the blood than there is out there in the lungs, and so CO2 basically forces its way out into the lungs. So once again, go back over that on your own. Spend a little time with that. This is how it works. There's no magic going on here. It's all about pressures, isn't it? And all about this cool thing with the chloride shift and the reverse chloride shift, and about the bicarbonate ion being the way to carry carbon dioxide through your body so that it can be released by the cells and then exhaled by the lungs. This is just so damn cool. This is physiology, kids. This is the shit right here. So go over it a few times. I normally ask questions about this on quizzes and exams. I think this is an outstanding example of physiology, and I want you to really know it and learn it and show me that you understand it, okay?